Hi guys, we're going to be talking about inscribed angles today in a circle, which you've already taught about one type of angle inside of a circle called a central angle, which central angles are slightly different than inscribed angles, and your mind is about to be blown, so wait for it. Alright, we're going to learn about inscribed angles. So, an inscribed angle is an angle whose vertex of the pointy part of the angle is on the circle. So, if you look at this angle, the vertex point is on the circle. Holy hot dog, right? Okay, so this is an inscribed angle. Okay, and inscribed angles have something called an intercepted arc, which an intercepted arc is the arc that is created by the intersection, of the inscribed angle and the circle. So basically the arc that runs in between where the angle starts and ends on the circle is the intercepted arc. So this arc starts where the angle kind of starts on the circle, and then the arc ends where the angle also ends. So starts and ends where the angle hits the circle. So that is called the intercepted arc. Be careful, slightly different than intersected, kind of the same concept though. Alright, and the inscribed angle theorem. So, inscribed angles have a special relationship with their intercepted arc. So, the measure of an inscribed angle is half the measure of the intercepted arc. So if you know the measure of the intercepted arc, if you divide that bad boy by 2, bam, you'll have the measure of the angle. Guys, and then you could also reverse that process. So if you know the measure of the inscribed angle, if you double it or multiply it by 2, then bam, you'll get the measure of the intercepted arc. Okay, so like in this picture, angle ABC equals half the measure of the intercepted arc AC, or the other way, the measure of arc AC equals 2 times the measure of angle ABC, which is the inscribed angle. Wowza, right? Am I right? Of course. Guys, now this orange angle, we've already talked about this type of angle. What type of angle has a vertex point on the center of a circle? It is a central angle. And what is the relationship between a central angle and its intercepted arc, or the arc that starts and ends where this angle hits the circle? Well, central angles equal the measure of their intercepted arcs. Okay, we've already talked about that concept. Okay, so knowing that, since the arc is the same measure as the central angle, that means we can kind of compare the relationship between the inscribed angle and its intercepted arc to the inscribed angle and the central angle. Guys, so since the central angle and the intercepted arc are the same, that means if you have a central angle that intercepts the same arc as an inscribed angle. So if you guys see your angle ABC and angle ADC both intercept arc AC. So they both have arc AC running through the angle. So if that is the case, that means that the measure of the inscribed angle, if you have the measure of the central angle, then you'll get the inscribed angle, or vice versa. If you double the inscribed angle, you will get the central angle. So that will only work though if the central angle intercepts the same arc as the inscribed angle. If there's a central angle in a circle, and it has nothing to do with the intercepted arc of the inscribed angle, then there's no relationship. But that is something to keep in mind if you see something like this happen. Alright, so go ahead and pause the video and watch example 1 and 2, and use the inscribed angle theorem to help you solve these lovely example problems. Oh man, those were just too easy, right? So we need to throw some more properties at you to make these example problems a lot more challenging. So let's talk about some more inscribed angle properties. Guys, so if you have inscribed angles of a circle and they intercept the same arc, that means they're congruent. So let's talk about why. So inscribed angle ABC, which we know this is an inscribed angle because the vertex point hits the circle. Okay, this angle intercepts arc AC, but angle ADC also intercepts arc AC. Whoa, right? I know. Alright, so since both of these inscribed angles intercept the same arc, that means they have to be congruent. Because if you know the arc's degree, since both of these are intercepting the same arc, you divide by 2, to get both of these angles. So that means they're both the same. Guys, so the measure of angle B, or angle B, is congruent to angle D, both of these, which means their measures are equal because they both will intercept the same arc, arc A to the C. Pretty cool, right? All right, and our second additional inscribed angle property is when we have a semicircle. So, if an inscribed angle's intercepted arc is a semicircle, then it measures 90 degrees. So, let's talk about why. So, this diameter will break up the circle into two half circles, which are called semicircles. Okay, and then the total amount of degrees in a circle, if you didn't know, is 360. So if I divide that bad boy in half, how many angles, what is the degree of the angle of a semicircle if it is half of a normal circle? It is 180. So a semicircle, or half the circle, is 180 degrees, okay, which that could be on either side of the circle. So if we have an inscribed angle whose intercepted arc is a semicircle, okay, the relationship between the arc and the inscribed angle, what do you do to the intercepted arc to get the measure of the inscribed angle? You do have it. So what's half of 180? It is 90 degrees, which means if an inscribed angle intercepts a semicircle, it has to be 90 degrees. So you could probably figure that out without knowing this theorem, but, you know, it's helpful to know. And if you remember it, you don't have to think through it. You can just automatically know. So if you ever see an inscribed angle intercept a semicircle, you can just already know it's 90, like if you remember that. If you don't, you can kind of figure it out. But, pretty cool, right? Again, I know, because we agree on everything. But anyway, so we're going to be using both of those theorems and properties to help us solve example 3 and 4. So go ahead and pause the video and watch example 3 and 4. Oh man, you guys, our last property we're going to talk about is when we have an inscribed quadrilateral, which inscribed figures are within another figure or polygon or shape of some sort. Okay, so in this case, we're going to have a quadrilateral inside of a circle. So it's an inscribed quadrilateral. So the opposite angles in an inscribed quadrilateral, which is a quadrilateral inside of a circle, are supplementary. So opposite angles, so B and D are opposite angles, which means they're supplementary because we have a quadrilateral inside of a circle. Now this only happens when a quadrilateral is in a circle. Okay, in a normal quadrilateral, opposite angles do not necessarily add up to be 180, so watch yourself. The demon cats will get you if you assume that about a quadrilateral, so watch yourself. Guys, and also, so that means the measure of B and D up to 180. Also, A and C are opposite angles in this quadrilateral inscribed in a circle, which means they will also add up to be 180. So we're going to use this lovely property in our final example problem, example 5. Guys, in example 5, I let the demon cats get to me, and I did a really poor job of writing down example 5. Like, I did it, and it looks okay, but it's kind of hard to read. So I might just pause the Prezi right here and copy this down off the Prezi, because you're going to laugh at me. It's kind of embarrassing. My example 5 did not turn out well when I put it on a piece of paper. So look at this picture, copy down example 5, and copy the directions, because I messed up the directions too. I know, laugh in my face. The demon cats were seriously getting to me on this one. So I didn't mess up any of my math though, so that's good. But the picture looks awful. So go ahead and pause the video, copy down the slide, then watch example 5. Well, I hope you guys enjoyed inscribed angles as much as I do, because I love inscribed angles. Circles are fun, and inscribed angles just make it even more fun. Nice job, you guys.